Dear friends, welcome to this electrical engineering knowledge sharing channel, AMP Power System. We are discussing UPS system. Under this session 9, we have already discussed various session or various videos. Now we have already started the UPS sizing, and under the UPS sizing, we have already completed video 78, where we have find out how to UPS kVA or kilowatt is to be decided based on the connected load on the inverter or UPS output. Now we are going to calculate the second subsystem of the UPS system, which is the battery. Now when we are going to sizing the battery, we have to know a couple of things about the battery. Now battery sizing also not only depending the capacity of the UPS, it also depend on the type of battery and the battery's various parameters. So we'll discuss all these points one after another, and also the load characteristics or the load current characteristics also has a great impact to the battery sizing. So for this video, that video number 79, we are going to discuss the battery sizing based on the constant load or constant current at the UPS. UPS current maintaining constant over a period. Now, when we are going to consider the period, we will be discussing in details how the period is to be selected. So let's start the sizing calculation for the constant current UPS battery. Now, when we are going to discuss the battery, first we need to know, the battery, various types of batteries available in the today's market. But for the industrial plant or industrial purpose, like a power plant, substation, petrochemical plant, still today we are using mainly two type of battery. One is a lead acid battery, another is a nickel cadmium battery. In the case of lead acid battery, it is mainly two types are available. One is called open type battery or tubular type, which is open type battery. Another is a seal type battery or BRL type battery. In the case of open type battery, this battery is producing hydrogen, and that hydrogen is getting out by evaporation, and then this battery is regularly put water to maintain a specific gravity of the electrolyte. But in the case of lead acid seal type battery, we do not add the water regularly, because this battery, what is happening, the technology is, in the battery positive plate, whatever the oxygen is getting produced, that oxygen is accumulated with hydrogen and producing water, and that water is absorbing the electrolyte. So your electrolyte is maintaining constant specific gravity. In that case, we need not to add water regularly, and there is a regulated valve on the battery. That valve, actually what it is doing, if this battery is subjected to the vigorous discharge charging, like a boost charging, or if the chemical reaction takes place very vigorously, then it may produce a hydrogen such a level which cannot be accumulated completely with the oxygen. In that case, the additional gas is to be evaporated or to be evacuated from the battery cell, from the battery container. So that is done through a regulated valve. There is a valve which is getting open under the pressure. So once the pressure is going beyond the limit point, then the valve is getting open and the additional gas is getting discharged from the battery. So that is called valve regulated battery, which is nowadays widely used in the industry. So in the other type of battery, which is a nickel cadmium battery, that also is widely used. Now the application, whether we use the nickel cadmium battery or lead acid battery, that depend on the various parameter of the load. Nickel cadmium battery advantage is life is long, and it can deliver at constant voltage for a longer time than the lead acid battery. Lead acid battery, after discharging certain time, battery terminal voltage gets dropped, so load cannot get the required voltage. So, but if you need a long duration constant voltage in the load, in that case lead acid battery is a greater preference. So we will discuss all these things in details. So before going to battery, which type of battery we will go to select, before that we need to know some of the parameters of the battery. When we discuss about the battery, couple of parameters, any engineers or technical expert or technical people, they know about the battery. First is what is the technology we use for the battery defining or specifying a battery. Mainly we define four parameters of the battery. One is the battery capacity. Now battery capacity we measure in terms of ampere hour. That means a particular battery, if I say it is to be discharged at the rate of 10 ampere and I need for 10 hours, then the capacity of the battery will speak in this language. Capacity we always define in terms of ampere hour. Ampere into hour, that is called ampere hour. That is A is the unit. How it is defined? Suppose a battery as a 10 ampere current a battery is delivering for the 10 hour, then the capacity of the battery will give 100 ampere hour. So that is one of the parameter. That is called the capacity of the battery. Suppose the same battery, if I take the 10 ampere battery and if I say this battery to be discharged over a period of 8 hours, then whatever the ampere hour of the battery, that will be 80 ampere hour. This way we define the capacity of the battery. That is the first terminology for the battery. Okay. So one of the important parameter we need to know before discussing the battery is the battery capacity. And the capacity is measured in terms of ampere hour, means how many ampere current is delivering and over what period. That multiplying that to factor will give the capacity of the battery. That is the first parameter. Then the second parameter or couple of parameters is required after this. That parameters are related to the voltage. Now, when a battery, we go for the battery sizing or battery discussion, we need to know couple of voltage for the battery. When a battery is fully charged, in a fully charged condition, the battery has a voltage. That voltage we call the no load voltage. The no load voltage we define by V0. Okay. That voltage means battery is fully charged and battery has not yet connected with the load or load is not discharging the battery. That voltage we call the no load voltage. Okay. That is one of the terminology we use in case of battery or cell. Then we call the nominal voltage of the battery. That is a nominal voltage. That means at this voltage what is happening, battery is connected to the load and battery has started to discharge the current. So that is we call the nominal voltage of the battery. Nominal voltage. Then when the battery is getting discharging, so continually voltage is getting, after a certain time it will give a constant voltage. After that voltage will be gradually dropping. So during the dropping point, at what point will cut the voltage or at what point will allow the battery to stop discharging, that voltage where will not allow further discharge, that voltage we call the end cell voltage, VE, that is called end cell voltage. Okay, these are the three voltages for any battery we need to know before going into discussion for the battery sizing. That means how is it? Suppose if I draw the discharge characteristic, voltage characteristic of the battery, if we draw this side is a time, discharge time, this is a discharge time and this is a discharge current. If I say this way, this is a discharge current by the battery. So how is this? Suppose this is my voltage, it is called V0, that is no load voltage. The moment you connect the load, then battery voltage will from the no load, it drops slightly, then it will be maintaining constant over a period. Okay. So this voltage, when it suddenly drops, it is called nominal voltage. And in this nominal voltage, it will be maintaining over the time. Then after it will be discharging and it will go to zero voltage. During this dropping part of the characteristics, at what point, suppose I want to stop the discharging at this point. So this voltage, this point, this voltage will be called the end cell voltage, VE. So these are the three voltages of a car. So what the battery we have discussed two types of battery. One is the lead acid battery and is a nickel cadmium battery. In the case of nickel cadmium battery, advantage is this constant voltage discharging, it go further beyond and then it will get drop. So if you want a load is such a sensitive, it cannot take the voltage drop, then we have to go for the nickel cadmium battery because it can deliver longer time with a constant current delivery or constant voltage during the discharging of the battery terminal voltage can be maintained for a longer time. So these are the four parameters. Now, if you look into these voltage parameters for the two type of battery what we discussed, in case of lead acid battery, normally the nominal voltage is approximately 2.1 volt, approximately, in the case of lead acid battery. Okay, and the this is the no load voltage. In the case of lead acid battery, the no load voltage V0 approximately V0 2.1 volt, and if you go to Vn, that is approximately 2 volt. And the end cell voltage for the lead acid battery, normally we do not allow the discharge of the battery after 10% of the voltage drop, it depends on the load requirement. If the load is very sensitive, it cannot take more than 5% voltage drop, then we have to stop the battery discharging at 5% drop. But if the load is slightly less sensitive and it can accept the rated voltage below 10%, then we can allow up to 10% voltage drop. That means 2 volt is a rated nominal voltage. 2% of that means 2%, 10% of the nominal voltage means 2.2 volt. That in that case, end cell voltage will be 8.8 volt. So up to 1.8 volt will allow to discharge the battery. In the case of lead acid battery, these are the parameters normally we go. Sometimes it is instead of 1.1 volt, or sometimes we go up to 1.75 volt. But in the case of nickel cadmium battery, this characteristic is different. Nickel cadmium battery, in the case of nominal voltage, no load voltage, is approximately 1.4 volt. Okay, and when it go to the nominal condition, so it is 1.4 volt approximately. No load voltage, if you say 1.4 volt, then when it is going to discharge, nominal voltage will go to 1.2 volt. That is this is a V0, this is a Vn, and then we will allow up to discharge 1.08 volt or sometime 1.1 volt. Up to this value we will allow to discharge. This will be V, this will be Vn, and this will be V0. Like this is the nickel cadmium battery. So what about the battery we consider? Accordingly, we have to decide these parameters. Okay, these are the basic parameters for the battery. To when we are going to size the battery, this will be required. So once we know this type of characteristics of the load and these parameters, then we'll go for the selection of the battery. Which type of battery we'll go to select depending on the load. So suppose we are now considering lead acid battery. Suppose for our calculation purpose, we have selected lead acid battery. So in the case of lead acid battery, these are the parameters we have in our hand. That is, we know first we have to decide the ampere of the battery. What is the battery ampere hour required? Then we have to know what is the battery V0, what is the Vn and VE. That is, we know for lead acid battery, these values we know. It is 2.1 volt. This is a 2 volt. This is suppose 1.8 volt. These are the three parameters already we know from the lead acid. Once we know these three voltage parameters, then we have to know the ampere hour requirement of the battery. How much ampere hour we require for the battery, how we will decide that? That is the first part of the parameter. That is, we decide from the load requirement. Okay, how much load we have, or what is the size of UPS. We have already seen the UPS configuration, right? UPS configure, how is it? This is your UPS AC, this is going to DC, this is our battery, and then we have an inverter over here, right? And then this is the output. Here is the output is connected. So now when the battery is coming to picture, when this AC supply to the converter or the rectifier drop or fail, then there is no input power, then the battery will get discharged and it will deliver the power, and the output is to be maintained. So suppose this UPS is depending on the UPS output requirement, we have to calculate the battery sizing. That is the basic thing. Now this UPS capacity or the inverter capacity, we have seen in the previous video 78, we have calculated in kVA. Sometimes it is, if the load is in VA, we can calculate in kVA. If the load is in kilowatt, then we have to calculate the UPS capacity in kilowatt. That means kVA into, we have to multiply by power factor, then we will get the kilowatt. So this is the load. So if the load is in kilowatt, that is the extreme condition. So we are considering in terms of kilowatt. So if I have the load at the output, suppose a certain kilowatt, that kilowatt load if we have, then what is the input current is required. So input current, how I will calculate? This input current, if we want to require, this is a DC current and this is a AC output. So when this AC output, suppose X kilowatt AC output is required. So if I go to the output X kilowatt, what is the input? How will get the input? Kilowatt, we have to convert to kVA and efficiency. So this kilowatt divided by power factor of the inverter into efficiency of the inverter. If we divide this thing, then we will get the input kVA. That is the kVA required at this point, right? So if the output kilowatt is given, suppose this is X kilowatt is given at the output, how I will get the input to the inverter? I will divide the kilowatt by power factor, then I will get the kVA, and then we divide the UPS efficiency, or then I will get the input kVA. Once I get the input kVA, then I need to know the voltage at this point. Okay, what are the voltages? Suppose here the voltage is V, then what is the ampere required? Ampere required equal to kVA divided by voltage. Suppose the voltage is V, so this will be kilo ampere current is required. Okay, so these are the way I have to calculate the input current. So when we are going to discuss the inverter input, DC current or battery current, we need to know what is the output of the inverter based on the output, and then we need to know the inverter efficiency, inverter power factor. By getting this parameter, I can get the input kVA. Once we know the input kVA, then we need to know the battery voltage over here. What are the DC voltage over here? Once we get the DC voltage, I know the DC voltage, then I can calculate the battery, how much current is need to deliver the X kilowatt of power. So in this way, I can calculate the battery current at this point. But we have to calculate the ampere hour. So only ampere will not work out. Kilioampere means this will be ampere into 10 to the power 3, right? So how I will get this ampere hour? Now I need to know this kilowatt power or this amount of ampere this battery has to deliver for how many hours. That is our backup time or autonomy time of the battery. So how we decide the autonomy time? Autonomy time we decide based on the plant operation. This UPS we are purchasing or we are installing for a particular plant. That plant has a operational sequence. Now how this UPS coming into the picture, we have already discussed that every plant they have their normal generation for the normal power. Either they have their own generation or they are getting power from the grid. We have already seen this part. Now once this normal power supply, that means grid power supply or their own generation, either gas turbine generator or steam turbine generator or any form of own generation gets filled, then immediately what will happen? Every plant they have their emergency diesel generator. So it starts, and once the emergency diesel generator is start and the power is normalized, emergency power is normalized, then a plant getting going to normal all emergency and critical load gets served. So as UPS is under critical load, so UPS also getting power from the emergency generator. Now the moment normal power plant shut down, normal power generation shut down, and the generator starts, there is a time. It may be 15 to 20 minutes. So this 15 to 20 minutes I have to back up this UPS. UPS has to back up by the battery. That is one application. Second, it may happen that this normal power supply fail. Immediately emergency diesel generator failed to start. It is a mechanical device. This emergency diesel generator, there is a diesel engine. The diesel engine is a driver. It is running alternator, and alternating is producing current. But that diesel engine may fail to start. If that is because so many controls they have, if it failed to start, then what will happen? Till this problem of the diesel generator is not troubleshooted, or the normal power which is dropped, if that is not getting started, I have to back up my critical load by the UPS. So it may go 2 hours, 8 hours, 4 hours. We don't know. That depends on the plant operating condition and what type of turbines they have. If it is a gas turbine, it very quickly it can start. But if they have a steam turbine, it will take longer time, maybe 6 hours, 8 hours it may take to start up once the shutdown is there. So depending on the plant condition, the backup time to be decided. So let us consider at this moment, it is a gas turbine plant while the diesel generator is emergency generator. So once the gas turbine drops, then the emergency diesel generator should start up. If the emergency diesel generator failed to start, then within the 2 hours time, hopefully either normal power supply or emergency generator will come into the picture. So we will consider the UPS has to cater power for 2 hours. We are considering in that way. So if we consider the 2 hours, then what about the ampere we have got there in the previous calculation from the kilowatt? What are the X kilowatt? We got the output, and then we have divided by power factor. Then we divided by efficiency. Yeah. Then we get the kVA, right? This kVA we divided by battery voltage, we get a kiloampere. That is equal to ampere into 10 to the power 3. That ampere into multiplied by, suppose this hour is H, 2 hours if I consider, then that will give the ampere hour of the load requirement. It is the load requirement ampere hour. In this way, we calculate the load ampere hour. Okay. Once we calculate the load ampere hour, then we have to calculate the battery requirement. Now, when we are going to discuss the battery requirement, we need to know couple of parameters from the battery manufacturer. What are those parameters? Because those parameters we do not have in our hand. There is a couple of standards. The standard which we mainly use for the battery sizing, that standard we call is IEEE standard. In the case of IEEE standard, there is IEEE 4851 standard we have, which we follow for the battery sizing calculation. If we look into the IEEE 485, they have mentioned there are 4 parameters we need to know before sizing the battery sizing. Now, out of these 4 parameters, one parameter is in our hand. That parameter which will be decided by the designer or the engineer who is calculating the battery sizing, and after the discussion with the plant owner or the parties involved in this plant, after discussion with that, one of the parameter we decide what are the safety margin we will keep in the battery. In the case of UPS, we have seen that we have said that sometimes depending on the load, future load growth, sometimes we consider the UPS capacity 25% extra margin. If we consider 25% extra margin, in that case, battery has to cater for that. So battery also should have that 25% margin. But if we consider we'll consider 15% margin, 15% additional capacity we put in the UPS to take care of the future load growth. In that case, the battery also has that 15%. So there will be one factor we call is safety margin. Safety margin of the battery. The safety margin, it could be 1.15, it could be 1.2, it could be 1.25, depending on the design engineer and the party involved in this after discussion of this. Presently, suppose we are considering it is a 1.2% or 1.1% is my battery safety margin we need. Okay. So this is one of the factor, or you can say there is a safety margin, SM, safety margin, KSM, that we are considering 1.15 for the battery sizing. Okay. And the UPS also has a 15% margin. That is one of the point. Second point is, this will be decided by the designer. But in addition to this, there will be another 3 parameter we need to know from the manufacturer. What are those 3 parameters? One of the parameter, first parameter we say, it is a rate of discharge constant. Rate of discharge. Okay. That is one of the parameters. This parameter we call a rate of discharge factor. This is one factor. I'll explain all this. Second factor we call is a depth of discharge. This is a depth of discharge. This is another factor. Third factor we call the temperature factor. Okay. Temperature factor. What are these factors? Let us start from here. Now, you know this each battery, how it is producing current, there is an electrochemical reaction. By doing the electrochemical reaction, this battery is producing through the electrolyte and the electrode, the electrochemical reaction takes place and it produces current. Now, all the electrochemical reactions, how it depend on the ambient temperature, the temperature at which the reaction takes place. If the temperature you increase, automatically electrochemical reaction goes faster or it takes place more vigorously, and if the chemical reaction takes place more vigorously, it will produce more current. So if it produces more current, automatically what will happen? It will capacity also, if the current got increased, automatically ampere hour also got increased, so it will give more ampere hour. So as the temperature goes up, each battery will give more ampere hour capacity. Similarly, if the temperature goes down, it will happen reversely. As the temperature goes down, electrochemical reaction takes place slowly. Then what will happen? Then automatically current will drop. If the current drops, then automatically ampere hour also drop. So we can make out that any battery, whatever the ampere hour is specified, that ampere hour is to be given in a specific temperature. And if the temperature of the ambient is different from that specified temperature, then the ampere hour capacity can be increased or can be decreased. If it is decreased, then to meet the requirement, I have to put additional capacity inside. So there is a factor or margin is required due to the temperature. So most of the manufacturer, they specified their capacity battery when they are delivering capacity, selling the battery. They said my battery has this amount of ampere hour capacity. They specified 3 parameters. One parameter is what are the discharge time, what is the temperature. Suppose, and in most of the manufacturer, they define this rated condition as 25 degrees centigrade. That is the rated condition for most of the manufacturer. Most of the manufacturer, whatever the ampere hour they declare for their battery, that ampere hour is defined at the temperature of 25 degrees centigrade. Now, if the ambient temperature is different from this 25 degrees centigrade, then we have to multiply that ampere hour with the respective factor. That is a temperature derating or uprating factor. If the temperature is above this temperature, then it will be derating factor. We don't need suppose this particular battery has a capacity 10 ampere hour at a 25 degree centigrade. If my temperature is 50 degree centigrade, then this same battery can give more than 10 ampere hour. So that 10 ampere hour requirement, I can reduce the factor by factor. But if the temperature goes down, then what will happen? 10 ampere hour is my requirement. At 25 degree centigrade battery is offering. Now my temperature is suppose 21.1 degree centigrade. Then what will happen? It will not give 10 ampere hour. It will give less than 10 ampere hour. But my load is 10 ampere hour. So I have to increase that capacity, 10 ampere hour to be increased. So there is a elevated factor. Then the KT will be positive. So I have noted down this temperature factor from the IEEE 485. So here you can see at 25 degrees centigrade the factor is 1. Here is the KT. This is the KT value. KT is 1. At 21.1 degrees centigrade the KT is 1.04. That means the temperature goes drop. Immediately I have to increase the capacity by 4%. If the temperature goes further down 15.6 degrees, the ambient temperature, then I have to increase the capacity by 11%. The factor is 1.19. If the temperature is 10 degrees centigrade, then I have to increase by 19%. At 4.4, it is a 30% capacity I have to increase. This is the KT factors. So if the temperature below the rated condition, in that case, the capacity will be increased by this factor. So this one of the factor either you can get from IEEE or better to get from the manufacturer who is then going to deliver the battery. From him we can get this temperature derating or uprating factor. So this is one of the factor we need to know before starting the battery sizing calculation. That is the first part, KT. Second part is what we have said, that this battery, when a vendor or any battery is delivering or he is offering the battery, he is delivering the battery at a particular capacity. He is mentioning certain capacity. This capacity of the battery normally we designated by suppose C8 or C10 like this. You will see, if you see the battery catalog, you can say this type of terminology is there, C8, C10. The meaning of that, the battery which the vendor is offering or the manufacturer is manufacturing, if we say my C8 capacity is suppose 80 ampere hour. He said my battery is a C8 capacity 80 ampere hour at the rate of 25 degrees centigrade. He will mention in this way. That means this particular battery, suppose this is a type battery, one particular type of battery. He said my A-type battery C8 is 80 ampere hour at 25 degrees centigrade. Meaning of that, this battery, if I operate at 25 degrees centigrade and I will discharge the battery for a period of 8 hours. This 8 is meaningful. This 8 means I will discharge the battery to be discharged over a period of 8 hours. Then only it will give a 80 ampere hour. Means how much ampere? 80 ampere hour discharge over 8 hours means it will give 10 ampere. So I will get this C8 battery of 80 ampere hour capacity at 25 degrees centigrade. I will get only 10 ampere for 8 hours. Now if I don't discharge the battery over 8 amperes, if I discharge for another hour, then it may not deliver 80 ampere hour. So similarly, suppose the battery that vendor said my battery C10 capacity, he is defining his battery at C10 capacity. C10 capacity is 100 ampere hour. Okay, 100 ampere hour. It means this battery is rated for 10 hour discharge. So it can discharge over 10 hours, then it will give 10 ampere. Okay. Now, suppose I have a load of 20 ampere. Suppose I have a load, I need a 20 ampere current battery to be delivered. Then I thought, okay, I have a 100 ampere hour battery. I don't know the meaning of this 100 ampere hour battery. I need 20 ampere. So what I'll do, I will put 100 ampere hour battery and I am drawing 20 ampere. So I thought, okay, it will give how much? 5 hours. And my load requirement is 5 hours. So I said, okay, I need 20 ampere current for 5 hours. So 5 into 20, 100 ampere hour. I have a 100 ampere hour battery, so I can use this battery. But this battery is rated for C10, means it will give 10 ampere at 10 hour discharge. But now instead of 10 ampere, I am increasing the capacity double. I am taking 20 ampere. And I am thinking as this ampere hour it will deliver, it will give 5 hours. But actually, it will not give 5 hours. We may see that after 3 hours, battery has completed its discharge. It has no more power in the battery. Battery has after 3 hours, it is completely discharged. Means a battery which is specified for a particular hour, for a particular current, if you increase the discharge current, then battery will not give the backup autonomy hour in proportional to this 10 hour capacity. Then it will give a different ampere hour. So how much ampere hour will be reduced? How I will know this thing? This is given by the manufacturer in the rate of discharge factor, in the form of rate of discharge factor, or in the tabular form. A particular battery which is rated for 8 hours or 10 hours, if we discharge the battery over another period of time like 6 hours, 4 hours, 2 hours, 1 hour, 30 minutes, 15 minutes, how much current and how much ampere hour it can deliver, manufacturer provide a curve, or they give the tabular form. From the tabular form or from the curve, we can calculate a factor which is called rate of discharge factor. So that is the important thing. Rate of discharge factor is deciding if a specified battery for a particular hour and particular ampere, if I use that battery for higher ampere, more than rated ampere, in that case, what will be the backup time and how much ampere hour it can give on that higher current, that figure given by the rate of discharge characteristics or rate of discharge table. So that I have taken one of the battery, a specific battery, this chart, how does it look? This is the rate of discharge characteristics shown in the tabular form. Here we have a 3 parameter. One is the this is the discharge time, and how much hour it can deliver. This is the discharge current and this is the capacity. Suppose I have a battery, a specific battery. Suppose this battery is a 8-hour capacity battery. In 8-hour capacity, discharge time 8 hours is the rated condition, and it is a 13 ampere current it can deliver, and it can deliver 13 ampere. How much ampere hour of the battery? 104 ampere hour. This is the capacity of the battery specified by the vendor at the rated condition. This battery is a 8-hour discharge C8. It is a C8 battery, and capacity is a 104 ampere, and it can be given 13 ampere rated current. This is the battery. Now, if the particular battery, this is a ampere hour, 104 ampere hour. If this specific battery, now if I discharge over 6 hours, how much maximum current it can give? It will not give. Now I am discharging the 6 hour, discharge time 6. That means 104 by 6, 6146. How much it is coming? 6444, 17 point something, right? It should give 17 point something, 17.2 or 17.3 ampere. If I take if it gives in proportional, but no, you see it is giving only 16 ampere and corresponding ampere hour is 96. That means the battery which is rated for 104 ampere at the rated condition, the moment I increase the current from 13 ampere to 16 ampere, so instead of giving 104 ampere hour energy, it is giving only 96 ampere hour. So there is a reduction. How much reduction? That is 96 by 104. This is the percentage reduction. This is the amount only I am getting. That means here nearly 5% power I am not getting from the battery. I cannot take that ampere hour. So this is one. Now you go further. You go for 4 hours. In the 4 hours, if you take this 104, how much it should give? In 4 hours, as per if it is a proportional, it should give 26 ampere, right? But you see here, I am getting only 22 ampere. and corresponding ampere hour 88. So I am not getting 104, it is getting less ampere hour. So in this way, if we increase the current, you will see it will be further reduced. You see, if I go for 1 hour discharge or 2 hour discharge, how much it is giving? It is giving only 74 ampere hour, whereas my battery is a 104 ampere. So I am getting about only 60% of this power. 60% of the rating condition ampere hour I am getting when I am discharging the battery about 3 times rate. 3 times. It is 13 ampere is the rated condition. I am 3 times I am overloading the battery. At that moment I am getting only 74 ampere hour. So from this way, you see here 30 minutes I am getting only 97. For 1 hour, how much I am getting? 1 hour I am getting only 58 ampere and 58 ampere hour. So I am getting half. When I am getting 1 hour, I am discharging the battery for 1 hour, I am getting maximum 58 ampere. Over a period of 1 hour means 58 ampere hour, where my capacity is 104. It is nearly 50% of this power I can withdraw. So that means here is a one factor is here. What is that factor? The rated condition of the battery 104. But if I discharge in the higher rate, then I am getting different. Suppose in this 2 hour I am getting 74. So if you divide 74, this will give 1.4. That means I need 40%. I am getting 40% less current over here. Or if I want to draw 104 ampere hour, I have to multiply this by 1.4. Means if I take this particular battery, this 104 ampere hour battery, one assumption it will give is rated condition. But as it is giving 74 ampere hour, so I have to multiply this requirement into 1.4 to get 104. So here this depth of rate of discharge factor is a 1.4. Here it is, you see, for in case of 1 hour discharge, this factor is about 1.5. So this is another factor we need to know from the manufacturer. So the third factor is a depth of discharge. What is the depth of discharge? Depth of discharge means here, you see, we have said that suppose this battery is a 104 ampere hour battery, 104 ampere hour, condition 13 ampere, it is delivering 8 hours. So after 8 hours, what is happening? After 8 hours, what is the battery voltage? The battery voltage drop down to 0. What we have drawn in the curve, the battery voltage drop down to 0. This is the voltage, this is the time. After the full discharge of 8 hours, battery voltage becomes 0, right? The B becomes 0. B end voltage becomes 0. But we have said already, this battery, if the end voltage becomes 0, that battery will not work for us because I have to supply the inverter required voltage. If the inverter is 24 volt input, I have to give the 24 volt input, but here voltage is getting 0. That means I cannot discharge up to the 0 voltage. That means depth of discharge, I cannot go to the end. I have to stop it somewhere else. That is our end cell voltage. When I am stopping at end cell voltage, what is happening? It cannot give the full capacity. At this, when this battery is a no load condition, it can give the full ampere hour. But as you dropping the voltage, then automatically what is happening is capacity gradually reducing, ampere hour gradually reducing. If you go up to the 0 voltage, this is your 0 voltage, okay? V0 equal, here this direction is V. So at that time when the discharge voltage is 0, then I am getting this amount of ampere hour. Suppose this is ampere hour. And when the discharge voltage, suppose this curve coming down like this, okay? Now I am getting the complete ampere hour. Now if I end the voltage over here, suppose this is my voltage. At this voltage I am dropping. At this voltage, this is the no load voltage. It is a V0, okay? And this is the VE. If we drop at this voltage, how much ampere hour I will get? I will get this ampere hour. I am not getting the full ampere hour. So we have already said that we cannot go this VE below 90% of the VN nominal voltage. So when I am ending the voltage 90% of the nominal voltage, most of the manufacturer they have to declare how much ampere hour I can draw from this rated condition. Most of the manufacturer they say normally up to 80% of the capacity, 80% of the capacity, once you draw to the up to 80% of the capacity if you draw, then the battery voltage will come to the nearly end voltage, end cell voltage, that is 1.8 volt. If we suppose in the case of lead acid battery, if I discharge at 1.8 volt, it can deliver approximately 80% of its capacity. So there is another factor is coming, KDOD. K DOD is a, that is a 80% means 1.2. That means if I consider K DOD, in that case, whatever the battery capacity they have declared, over that declared value, I cannot extract entire value. So if I have a requirement of 100 ampere, I have to consider the battery 120 ampere hour to cater for this discharge, depth of discharge factor. This is another parameter. And the fourth parameter is your, another parameter we have to consider, that is your aging factor. The battery has another factor called aging factor. What is that? You know, battery when it is discharging, for putting a new battery, then every 6 months we do the capacity test of the battery. Suppose I have a 100 ampere hour battery, so I need to know how that capacity is maintaining of the battery. I am regularly charging the battery, discharging the battery and using the battery. So every 6 months we do the capacity test of the battery. When manufacturer, most of the manufacturers, they recommend when the battery capacity drop down to 80%, drop down to 80 for 100 ampere hour, after testing, if we say after suppose 10 hours, we see the battery capacity has dropped down to 80 ampere hour. Then the manufacturer is recommending don't use this battery, discard the battery and replace the new battery. That means I have already reduced how much? 20%, 20 ampere hour, means 20% ampere hour it has reduced from the original capacity over the time. Okay, in that case, this, when I am designing the battery, I have to suppose this battery has a 20 years life, but after 10 years it has happened. So rest 10 years I cannot use this battery. So this requirement, additional requirement due to capacity depreciation, I have to include in the battery capacity calculation. That is we call aging factor. And most of the manufacturers, they call the aging factor, you put 1.2. Then it will get the right figure. So this is another parameter to calculate the battery. So these are the 5 parameters we need to consider when we are going to battery sizing. One is a temperature derating or uprating factor, rate of discharge factor, depth of discharge factor, aging factor, and the safety margin. On these 5 parameters we decide, then we can calculate the battery sizing properly. So now I am doing one numerical calculation for showing how to do this. Suppose I have a UPS system, that is a 20 kilowatt UPS system. Okay, how is that? We have already seen it. This is AC supply, battery is connected over here. This is a battery, and then I have an inverter over here, and then this is the load is connected over here. I have a 20 kilowatt load at this point. Okay, and I am considering this inverter power factor, the load power factor. Load power factor is 0.85. Okay, 0.85, and efficiency of the inverter is 90%. Okay, I am considering in this way, 90% is the efficiency, means 0.9 is the efficiency factor. So what do I have to do? We have already said, first I have to calculate the how much current, and we are considering this battery is a 24 volt battery. This is our consideration. Okay, so now we have already seen if the load is kilowatt, then we have to calculate the kVA first. How much kVA? 20 kilowatt load divided by power factor 0.85 into efficiency 0.9. So that will give me a kVA. That will give, if you calculate this thing, it will come 26.14 kVA. That will be given the input kVA over here of the inverter. Input kVA for 20 kilowatt output power requirement, inverter input kVA is a 21.4 kVA. Right? Now at this point, that means this amount of kVA I have to drop over here. Now this is a DC. This current DC current kVA means how much? kVA means ampere into kV or voltage into kiloampere. So now this voltage is 24 volt we have set. That means if I calculate the current over here, so how much the current? Current kiloampere, that equal how much? kVA divided by voltage. So kVA how much? This is a 26.14 divided by how much voltage here? 24 volt. So if you calculate this thing, I will get 1089 ampere. This is the current I need at this point at 24 volt. That means battery has to deliver this 1089 ampere current at this point. Now if the battery has to deliver 1089 ampere current at this moment, and this load, what is the backup time of the load? We are considering backup time of the load is hour is 2 hours. This load, this battery autonomy is required for 2 hours. on the normal power supply fail, this power supply got failed, this is not available, then with up to 2 hours, if the battery give the power to the load, up within that time, either the normal power supply will come back or the emergency generator will come back. So my backup time is 2 hours, and how much current is required for the backup time? 1089 ampere. So if I now calculate how much ampere hour I need, then what is the coming either? Then the required ampere hour or load ampere hour, we can say load ampere hour how much? That is equal to 1089 into 2 hours. This is the ampere and this is a 2 hours. So this is 2 hours. How much it is giving? It is giving you approximately 2179 ampere hour is required. So this amount of load ampere hour I need, or the inverter at this point, this amount of ampere hour to be delivered by the battery. Okay. So, and if I am considering this battery system is working at a temperature of 21.6 degrees centigrade. My required operating temperature 21.6 degrees centigrade. So what is the case now? This is the ampere hour I need to deliver by the battery, and battery is operating at 21.1 degrees centigrade. And at that condition, what is the battery? Suppose I have selected this CG, this particular battery, CG10 battery I have considered. CG10 battery, how it is defined? It is a C8 capacity is specified. The manufacturer has given me CG10 battery in terms of C8 capacity. That means how much? C8 capacity means 8 hour capacity. It gives 104 ampere hour, right? At 10. So I have to now calculate all these factors. First, rate of discharge factor, how I calculate? Rate of discharge factor, I will calculate. My discharging time requirement is a 2 hour, right? This is my discharging time, 2 hours. And my battery discharging time given at 8 hours, this is defined, this is offered by the manufacturer. So 8 hour it is 104, but actually when I am going to discharge at 2 hours, this battery is giving only 74 ampere hour. So I am getting out of 104, I am getting only 74. So what is my rate of discharge factor? Rate of discharge factor equal to 104 by 74. That is my rate of discharge factor. If you calculate this, it will come about 1.2. That will be my rate of discharge factor, right? Then second point is, it will be coming 1.4, not 1.2, it will coming 1.4. This is coming approximately 1.4. This is the rate of discharge factor. Then second factor is the depth of discharge, KDOD. KDOD, we have seen how much most of the manufacturers, they say his depth of discharge, if we discharge at the end cell voltage, 80% of its capacity it can deliver. Balance 20% ampere hour, it will not deliver. That means 20% margin I have to keep. So this depth of discharge factor is a 1.2, right? 20% margin I have to keep it. So that is the depth of discharge factor. Then the aging factor already we have calculated. We have said aging factor, when the capacity drop down to 80%, then we do not use the battery. That means the 20% that drop, that to be increased initially. So there is a aging factor, K aging, that is also 1.2. This factor also we know. And the safety margin we have already considered, KSF is equal to 1.15. This is our safety margin. And this system is operating at temperature of 21.1 degrees centigrade. At 21.1 degrees centigrade, what is the temperature factor? KT equal to 1014, 1.04. This is the KT. So I know all this parameter. Now, what about the capacity required? I am deleting this part. My capacity requirement is 2179 ampere hour. That is my load requirement. I have to meet this ampere hour. This is my ampere hour requirement. To meet this ampere hour, how much ampere hour battery I need for C8 battery? So first, how I'll calculate this is the uncorrected factor. It is an uncorrected capacity, we can say. So my corrected capacity, C corrected, that equal to how much? C uncorrected. This capacity multiplied all this factor. First I multiply temperature factor K104. Then I will rate of discharge factor 1.4. Then I will multiply depth of discharge factor 1.2. Then I will reach the safety margin 1.15. If I all multiply this thing, it will give 5352 ampere hour capacity of this battery is required. Okay, that is will come is 5253 ampere hour considering all these factors. Now to get, that means 5352 ampere hour battery I need of C8 104 ampere hour battery. That means how many battery bank is required? One bank is giving is your 104. So to meet this 5352 ampere hour, how many bank is required? 5352 divided by 104. This will give how many batteries are required? 5352 divided 104. It will give you 101, means 102. 102 bank is required to get this battery to power this ampere hour power. Okay. So how the battery connection will be there? Now the battery, if I want to use this battery, this will be connection 102 bank is battery of required, that we have seen. Now if we want to get this bank, how it will be connected? So this is the battery. Okay. So these are the battery like this like 102 bank will be here. Okay. And then this all positive, this will be connected in parallel. Okay. This will be connected all in parallel. This is the positive bus. And the all negative will be connected together. This is the negative bus. Okay. And the load will be connected over here. Okay. So this is the, so this will be total 102 bank like this. This is 1, 2 and this will be 102. This will be connected in parallel and then it will give a required capacity of 5253 ampere hour at the inverter input. This will give at the inverter input over here. Now each bank, how many cell will be there? That depend on the inverter voltage. Here, what is the voltage? Battery is connected over here. Huh? What is the voltage over here? Based on that, what voltage we have considered? We have considered 24 volt. Now we are, what type of battery we are using? We are using lead acid battery whose nominal voltage is 2 volt. So to get the 24 volt, how many cells are required here? 24 by 2. That means 12 cells are required. So I have to connect here 12 number cell in series. That means this battery will be connected like this, 12 numbers. This is a number 12. This connected over here. This is the positive point and this is the negative point. There is a 1, 2, 3 and this is a 12 number cell. This is connected in series. Then across this terminal I will get 24 volt. This 24 volt 12 number cell connected in parallel, total 102 bank. Then I will get this 5253 ampere hour capacity. So this way I have to calculate the battery capacity. Okay. So this is, here is a one of the factor we have considered. My output load 20 kilowatt is a constant. This constant power is not getting changed over the time. But if this current is not constant, suppose this power kilowatt is not constant, it is changing. So and if we see the current profile here in this case, how is that? The current is constant over the 2 hour. This is a current, this current is constant. But in the case of, this is how much current? It is approximately 1059 ampere current. That is a constant current. But if the current is not constant, suppose the current is fluctuating in nature. Suppose the current is, suppose this is the current, then, or the current profile, suppose the current profile is like this. This is the current, then it goes off, it's maintained like this, it goes, then again it is goes up like this. Suppose this is a current, so this current is suppose 10 ampere. This current is suppose 50 ampere. This current again 10 ampere. Suppose this current is 40 ampere. My current is getting changed in this way over a time of suppose 2 hours. In that case, the current, we cannot go by that calculation because for each part, you know what is the difference, major difference over here? Each part, this rate of discharge factor will be different. Here the battery is maintaining this 10 ampere up to this time. But at this time, what is happening? Suddenly current goes up. So it has to deliver 40 ampere differential. That current maybe it is for only 1 hour. So in 1 hour discharge for 40 ampere, that will not, we have to calculate from the table how much ampere hour required for this. So for each part, rate of discharge factor will be different. So we have to calculate this rate of discharge factor, and from the rate of discharge factor, we have to calculate this individual part ampere hour, and then we have to sum it up. So that also will follow IEEE 485. We can do this calculation in the next video for the variable load. That video number 80 will do this. This is one of the things. Second, another part we have to mention over here, in the case of UPS calculation, we have done the UPS calculation based on the load, but we have not separately calculated the inverter capacity or rectifier capacity. In this connection, rectifier capacity determination, we have left the things with the manufacturer, because manufacturer will deliver the battery and he knows what is the intermediate voltage if there is no other load connected to the DC. But if you want to calculate the rectifier, then that calculation also, it needs some additional consideration, because we have seen the rectifier how it is connected. This is AC, this is DC, battery is connected, here is the inverter. So we have considered the UPS system calculation considering the inverter output current. But when I am going to calculate the rectifier, rectifier is not only giving the inverter input current, it is also giving the battery float charging current, because how the rectifier is working, rectifier is continually giving the float charging current to the battery. This is a float charging current, and at the same time it is giving the load current to the output. So this rectifier capacity will be sum of inverter DC current IN plus charging current of the battery, float charging current. These two sum will be giving the rectifier capacity determination. So if simply but in that UPS may be 20 kVA, UPS may be 20 kVA, but rectifier will not be 20 kVA. Rectifier capacity 20 kVA or 20 kilowatt plus the float charging current. For that, what was the kVA requirement plus the efficiency of this inverter, that also we need to consider in the case of rectifier calculation. So if you want to know more about this, you can put a comment, then I can put a separate video for the rectifier calculation. Otherwise, we'll proceed for the second phase of the variable load battery charging calculation. With this, I am concluding this video. It is slightly longer because I have to include all these things. So please go through this, and hopefully it will help all of you. And please keep it up. And thank you very much indeed. Thank you.